everyone. This is going to be your note set for conservation of energy and how we can calculate enthalpy change using bond energy. So we have gone over the law of conservation of mass before. We talked about that all throughout the stoichiometry unit, that matter can neither be created nor destroyed, only rearranged. The law of conservation of energy is very similar. Energy can neither be created nor destroyed. And so both of those things are utilized when we look at reactions, especially in reference to not only how many grams of particular reactants or products are used or produced at any point, but also how much energy input and how much energy output reactions take. So the first thing I want to say is that we can calculate something called enthalpy change. Enthalpy is just a fancy word for heat energy absorbed or released. It does have a specific unit, and that unit is going to be kilojoules per mole. And so that unit is going to pop up a lot over the next couple of weeks as we talk about energy and enthalpy alike. But basically, we can calculate that value using bond energy, which I'm going to go back and forth a lot between energy and enthalpy, but basically all this bond energy stuff is actually an enthalpic value. And as we get more into thermal, you will better grasp and better understand the difference between energy and enthalpy. But the basic thing you have to know for right now is that if you do a calculation like this and at the end everything is said and done and that enthalpy change pops out as a negative value, that means that overall the reaction is exothermic or releases energy. But if that enthalpy change at the very end and when everything is said and done is a positive value, then that reaction is going to be endothermic or it's going to absorb energy. And this thing right here, this is the basic formula for how to calculate enthalpy change. So we have this little triangle H over here. The triangle is the symbol delta, and that means change. H is the variable that we use for enthalpy. So quite literally, delta H stands for change in enthalpy. So if I want to calculate change in enthalpy, I am going to take the sum of the delta H values for my broken bonds, and I'm going to subtract out the sum of my delta H values for my formed bonds. So I'm going to color code this for you, and I encourage you to do the same. Any bonds that are broken are reactants. And any bonds that are formed are products. And we talked about this a little bit earlier this week and in past units. We've talked about the fact that when a reaction happens, all of our reactant molecules end up rearranging themselves into product molecules. And for that reason, we know that we have to break reactant bonds during a reaction, and then we have to form product bonds if we're going to produce something. So really what I'm telling you here is that if you want to calculate delta H, you take all of that reactant bond energy and you're going to subtract out all of that product bond energy. So again, that formula in the little tan box right there looks a little bit scary, looks like a little bit confusing, but again, all you're doing is summing your reactants, summing your products, and subtracting the two. That's literally the whole thing. So let's get up into the steps of how exactly you're supposed to do that. So down here, we've got a cool table. And that cool table is a list of bond energy, or more accurately, bond enthalpies that are stored in various chemical bonds. And we talked about on Monday that chemical bonds store potential energy. And so these values in this table are the energy or enthalpy values for various bonds. So for instance, if I was talking about an HH bond, so a hydrogen bonded to another hydrogen, that value would be 436 kilojoules per mole. If, however, I was talking about, let's say, an oxygen-oxygen bond, and again, this would be a single bond, then that value would be 146 kilojoules per mole. So again, this little table just allows you to find different bond values. And then down here, we see some bond values for double and triple bonds. So let's say that you want this bond, well, that's going to be 146. But if you wanted this bond, then you would have to look down on the bottom here, and that value would be 498. So again, those values are going to be different based on the strength of that bond. So if it's a single bond, a double bond, or a triple bond. Okay? Now, up here, we have a list of steps for you. That was a horrible start. When you are looking at a reaction like the one right here in the practice problem, there are a series of steps that you're going to have to follow to calculate enthalpy change and again figure out if a reaction is endothermic or exothermic. Step 1 is making sure that you have a balanced reaction, which we don't currently have down there. So just to briefly review how to do that, what we want to do is we want to go from left to right, one element at a time. So the first element that I see here is carbon. And in my C2H4, there are 2 carbons. Over on the right-hand side with my CO2 molecule, there's only 1 carbon, and that doesn't match, so I have to make it match by placing a 2 in front of my carbon dioxide. So that takes care of carbon. Next element on the agenda is hydrogen. There are 4 hydrogens on the left-hand side, only 2 on the right. So once again, I'm going to place a 2 there to make sure that there are 4 hydrogens on both sides. Next element is oxygen. There are 2 oxygens on the left, but we have oxygen in multiple places on the right-hand side, so we have to total them together. In our carbon dioxide molecules that we have, since we have 2 carbon dioxide molecules, there's 4 oxygens in there, and then we have 2 more from the water molecule for a total of 6 oxygens. So my coefficient that I have to put here is going to be 3. Now, step 2 in my cool process above, we did step 1, we'll check that off. Step 2 is to draw out the Lewis structures for each reactant and each product. And yes, you do have to draw out however many there are. So for instance, I just said that there are 3 oxygen molecules now because I put a coefficient 3. That means I need to draw 3 of them. You don't just draw 1 and call it a day, because if you do that, you're going to miscount your bonds later. So, once again, if you forgot how to draw out Lewis structures, allow me to remind you. I'm going to start over on the right, actually, because water is a Lewis structure that we draw a lot, so you probably already know how to draw it, but I'm going to take you through the steps just in case you forgot. To draw a Lewis structure, we want to decide what thing goes in the middle, and that is usually the atom that you have the least amount of. In this case, I would put oxygen in the middle, and I would put both hydrogens on either side. My next step of drawing a Lewis structure is going to be the electron dots for each atom. Hydrogen is in group number 1 on the periodic table, so we're going to draw 1 dot on each hydrogen. Oxygen is in group 16 on the periodic table, so we are going to draw 6 dots around oxygen. Remembering that you can only pair up after 4. Now, we are going to start drawing lines between the unpaired electrons on neighboring atoms, so that I see that there's an unpaired electron on hydrogen and oxygen, so I can draw a line right there, and there's another one, so I can draw that bond. Now, because of this cool 2, that means that I need to draw 2 water molecules, so I can just go ahead and recopy that one. All right. Now, I have 2 carbon dioxide molecules. So for the rest of these, I'm not really going to spend a lot of time going over how to draw Lewis structures for each one of them, because again, we have done this before. you should recall how to do this. But if you don't, you're free to look up online a how-to video, or you can ask me later. But carbon dioxide looks like this. And I have 2 of them. So I'm going to draw 2 of them. Now over here, I'm going to put my little arrow in. I have 3 oxygen molecules. Oxygen molecules look like this. And lastly, we have our challenge one. We have our C2H4. Now that one, I will remind you that if there is no clear central atom, you would put the 2 that you have the least of in the middle. And in this case, it's going to be both of our carbons are going to go in the middle. And then our 4 hydrogens are going to go equally placed around them. All right. Now, if you remember how to draw C2H4, you might already know this, but we end up with an actual double bond in the middle and then a single bond going to each of those hydrogens. We make that a little bit longer. So we have now done step 2. We've drawn out the Lewis structures for each reactant and product. In step 3, we need to add up all of the broken bond energies. So I'm going to switch colors really quickly. And I'm going to move this up a little bit so that we can see this table. So our broken bond energies is our reactants. So now I'm actually moving into figuring out my calculation, right? So I know that my delta H value is going to be the sum of the reactants minus the sum of the products. So we need to first figure out what kind of reactant bonds I'm even looking at here. So for my reactants, I'm going to look at all the Lewis structures that I just did. And immediately I notice that I have a bunch of bonds between H and C. I have 4 of them. I have 1 here, I have 1 here, I have 1 here, and I have 1 here. So I have 4 CH bonds. All right? Because again, I have 4 little sticks between C and H. The second type of bond that I notice is this double bond between the 2 carbons in that same molecule. So I'm going to add on my double bond. All right, then I have my 3 oxygen molecules over here, and each one of them has a double bond between 2 oxygens. So I can add on 3 of this bond. All right, so that is going to be my total for my reactants. And then what I need to do is add on my products separately. So on my product side, I'm going to switch colors to my product color. I notice that there are 1, 2, 3, 4 CO double bonds. So I would have 4 of these. And then I notice that there are 1, 2, 3, 4 OH single bonds. So all that I have done is I have counted up my bonds. I've told myself what I have, right? And so then now that I've done that, I can move on to figuring out what my bond energies actually are. And I'm literally going to do that by referring to my table over on the left-hand side, and instead of writing the CH, I would write a number there. So once again, I have my delta H value, and that is equal to, up here, I know that I have 4 CH bonds. So if we look at our table, we find that C and H line up right here with a value of 413. So I have 4 times 413 instead of that CH. Over on my table, I know that C double bonded to another C is a value of 602. So I'm going to add 1 602. I also know over on my little table that an O double bonded to another O right here is a value of 498. So I'm going to add on 3 of the 498. Then I got to total my products. So I have 4 of this C double bond O over here. That value is 799. I have 4 of that OH. O and H line up here and here, right at 463. So I have 4 of the 463. All right, now I have a bunch of numbers, so I have to combine all of my terms. So on my calculator, what I want to do is I want to add up all of these together, and then I'm going to add up all of those together, and then I will subtract them from one another. So now would be a really good point to try and pause that video so that you can do that calculation for yourself. But if you don't want to do that and you would much rather just watch me do it, we can do that as well. So we have 4 times 413, which is going to give me 1652. We have 602. And we have 3 times 498, which is going to give me 1494. If I add those all up together, 1652 plus 602 plus 1494, I get 3,748. Now I'll switch colors to blue to do the products. I have 4 of those 799s, and that's going to give me 3196. And I have 4 of the 463s, which is going to give me 1852. I add those up, and I get 5,048. Now, I'm supposed to subtract those two values. I'm going to do 3748 minus 5,048, and that gives me an answer of negative 1,300 kilojoules per mole. Because again, that is the unit that all of these are in. That is again negative 1,300. I know that 3 is a little bit messy, but that value tells us something. That value tells us that the enthalpy change overall is negative, and that negative is directional, meaning that it is negative because this reaction system right here overall experienced a net loss of heat energy, which means that it released that heat energy to its surroundings, which is why a negative enthalpy change means that this reaction is exothermic. So on the worksheet today, you need to do this process overall. You need to do the balancing. You need to draw out all the Lewis structures. You need to identify all of your bonds. You need to total your reactant and your product energies and subtract them. And you're going to do all of that to determine if a reaction is endothermic or exothermic, again, based on the sign of the number that you get at the very end. So I hope this video was helpful for you. Try your best at the packet. If you cannot find a bond energy, it's not listed in this table over here, or if I didn't directly give it to you, yes, you can look up bond energy values, but I will warn you against that for the most part, because on the internet, you're not going to find one static value for a lot of bonds. A lot of times it actually varies based on the other elements that that element happens to be bonded to at the same time, and so you may not always find consistent numbers. So basically what I'm telling you is if you have to look up bond energies online, proceed with caution. All right, let me know if you have questions.